For today's Tuesday training, I'm going to cover unloading devices. I'm going to concentrate just on clearance devices. In a couple weeks, we'll cover different types of devices such as in deactivation, but today it's strictly based on clearance. Okay, so we'll get started here. Just a quick recap on compressors. In general, when we talk about compressors, the amount of power it takes to compress the gas is broken into three parts. The friction losses, getting all the metal to move back and forth and overcome friction. Valve losses to push and pull the gas through those suction and discharge valves. And the adiabatic, which is ultimately how much horsepower it's going to take to compress the gas from suction conditions to discharge conditions. So that's the basis of what we need to overcome in terms of power. Now, sometimes the compressor becomes overloaded because we try to do too high of a volume or too high of a compression ratio. And because of that, that's why we need to unload a reciprocating compressor at times. Unlike some other devices like centrifugals and so forth that are pretty much limited on pinching suction pressure or changing the speed, you can do those also with a recip, but a recip has the advantage of allowing for different types of unloading devices right there on the cylinders to affect the amount of power required and affect the amount of gas being compressed. Ultimately, it boils down to what we'll call a PV card. And what that PV card is, at some point, we start over here at suction pressure. We compress the gas up to discharge pressure. At some point, we have to overcome the valves and push the gas out through the discharge valves. And then by the end of the stroke, we pushed all the gas out that we can. Piston turns around, re-expands. The pressure inside the cylinder starts falling down. That would be the expansion event. It falls down so far it actually goes below the suction pressure, and at that point suction gas flows into the cylinder through the suction valves, and we repeat the whole cycle. But here again you can see the breakdown between the adiabatic, the green, which how much power it takes to compress the gas, and the valve losses, which would be the red, the discharge at the top, suction at the bottom. Just kind of use that as a basis here, because when we get into the PV card, there's a couple things that would be important as far as how we describe how clearance affects horsepower and flow. When we talk about clearance, there's a base clearance and then there's additional clearance. So the base clearance is, when the piston's all the way out, for example, here on the head end, or all the way in on the crank end, what that does is obviously the piston can't hit the head back here, so there has to be some type of gap. There's a cavity up here that's going to feed into the suction valve, the cavity down here for the discharge valves, and a little bit of volume coming back to the first seal rings and where the piston nut might be. If somehow you could just push this piston down, seal things, and fill it up with liquid, you get a feel for how much volume is in there. And that becomes the base clearance. That's the minimum amount of clearance. Cylinder designers are trying to minimize that typically because it's always easy generally to add clearance. It's very difficult to get rid of clearance. So when we go to, if a compressor is overloaded, it's easy generally to add more unloading, more clearance to unload it. But if a compressor is not loaded up enough, then it becomes very difficult to get rid of existing clearance. Ultimately, like I mentioned before, this will boil down to the PV card, and I'm going to bring up a live PV card here before we get started on the clearance devices. Oops. Get to the right program. There we go. So this is that pressure PV card that we talked about. Again, here on the right-hand side, the compression event. At the top, discharge, valve open. On the left-hand side, the expansion event, and on the bottom, the suction valve event. If this is how much work we're doing right now, and the way of conceptualizing that is the area inside of this diagram here ultimately corresponds to the amount of power required to compress this gas. So as this area changes, the amount of power required to compress the gas will change. So think of that as just area comparable to power. What clearance does, I'm going to add some clearance to this PV card, and we'll see that as we add more clearance, in essence, the PV card gets skinnier. and the horsepower went down. It was close to like 280, 290 before. Now it's fallen down to about 130. As you can see, the original card, which is in the gray outline, has a lot more area inside of it than the newer, skinnier PV card. That's what clearance does. It basically skews the PV card, bringing in the compression event over more to the left, bringing in the expansion event more over to the right, effectively making this skinnier. Because of that, a couple things are affected. Obviously, one, the horsepower is. But the other thing that's affected here, the distance from where we start over here, where we started compressing the gas, to where we start pulling in suction gas again. The length of this line, so on the original, from this point way over here, all the way over to where this gray line crosses, that's known as the suction volumetric efficiency. That's an indicator of how much new gas we brought into the cylinder. As you can see on the skinnier PV card, the distance of that line from here to where the new one crosses is much shorter. Effectively, we brought in less gas. So as we added more clearance, not only did we reduce the horsepower, we brought in less gas. And that's what clearance does. It affects both horsepower and flow. And also, it affects it very efficiently. Of all the types of unloading devices out there, clearance is at the top in terms of efficiency. So if you can, the best way to unload a recip generally is to have clearance type devices. Now, I'm going to run through a variety of different ways of adding clearance, and those are the devices we're going to take a look at here real quick. Okay, the first one is if a cylinder already has ports in it. So here we can see the valves coming into the cylinder, but somehow the cylinder was cast or machined, so it had this hole going in down into the cylinder bore. And what they can do is just put in a solid plug to fill up that volume, or they could just put a cap on this to expose that volume. Or over here on the crank end, you can see that volume there, and then you put on a cap with a little bottle on top of it. Because nothing's blocking this port, this becomes added clearance all the time. So it's not something you can open and close, but it's there all the time, as far as having a fixed plug like this. This would be a situation where the cylinder is too big for the application and it needs a lot more clearance so that we can effectively use that cylinder all the time. But this is not the type of thing you would use to create a sequence of load steps so that you can load up or unload the compressor. This would be more of a permanent change. You tend to pick up the size of these, put them on there, and they're going to stay that way for half the season or indefinitely. And just zooming in on that a little bit, and here you can see a real plug that might get used. Okay. Another way of doing that without having to have a special cylinder that has that stuff cast or machined into it is to replace the front head. Instead of having a blank head now, you can have a head with multiple volume pockets in it. Again, these ones just have solid plugs or plain caps on them. Again, if you have a plain cap, the gas can come into this volume here and it sees it all the time. Again, nothing that we open or close, it either sees it all the time, or if you put in a solid plug that seals it, it doesn't see any of this added volume. Again, it's designed for more seasonal stuff where you might shut down, put these in, and they're in there for 6 months, or, the unit goes out and you expect major changes in 2 or 3 years, so they stay in there for quite a while, then you take them out. These generally would go off the front head, whereas the other ones were cast in the cylinders. This is where you replace a blank head and replace it with a head that has these pockets built into it. Okay, another way of adding clearance, you can see this a lot on high-speed units, especially OEMs when they ship new units, is what's called a valve spacer. And so I'm going to zoom in on this a little bit here just so we can see a little bit better. But here's your standard valve. In this case, it looks like it's a plate valve. Below the valve is this ring. So when this gets assembled and pushed into the cylinder, this ring lifts the valve up. So inside of this ring, there's a certain amount of volume. Again, that volume's always in the cylinder. So it's always adding more clearance, making those PV cards skinnier, always reducing horsepower, always reducing flow. When they don't need it, some of them have the design such that you can take this ring and now move it above the valve. So now the valve gets pushed down closer to the cylinder bore and the ring's on the other side. Now that ring on the other side doesn't affect the cylinder clearance because the valve terminates the clearance when the valve's shut. So if the ring's on this side, you get the added clearance, but if the ring's on the back side, you don't get that added clearance. Nice convenient way of adding clearance at the valve level, so you can get it or not get it. Another way of adding some fixed clearance to a cylinder is to put on what's called a head spacer. So whatever pocket or head might be out here already, basically you're going to put on a big ring and you're just going to push that front head out some more. And whatever volume's inside of this ring now becomes added fixed volume inside the cylinder head. This is a nice, convenient, inexpensive way of doing stuff. The drawback here, obviously, is that typically it can only be done on the front head here. It's hard to get a ring on the crank inside. So it has this advantage, relatively cheap, very easy to do, adds fixed clearance to the front head, but again, only for the front head. Another way that some customers have added fixed clearance in certain circumstances is to have what might be called a reversible piston. So if we take a look at this piston here, this three-piece piston, now it's kind of exploded so you can see the three pieces, but normally all three of these would be brought together and bolted tightly. So you have the front piece, the middle piece, and the cranking section. And as you look at the front piece, it's nice and smooth and everything. And so this is what would be inside the cylinder, compressing the gas, and whatever the situation was, that becomes the base clearance of that cylinder. If they needed more clearance, this piston has the ability that you can take this front piece and this back piece and effectively swap them or flip them around. And you can kind of see it here. If you can see the internal cutout of that ring, that portion of the piston, if you brought this one, that concept forward, you'll see it right here. So what was internal volume inside the piston now becomes external volume outside the piston. And now that volume becomes internal to the cylinder during the compression event. So you're just taking this part of the piston, putting it up here, taking this one, putting it on the back, and that exposes the internal volume to the external, adding more fixed clearance to that cylinder end. Again, all of these so far are typically long-term, semi-permanent changes. You have to shut down the unit, make all these changes, bring the unit back up. It's not something you do every minute, every day, every week. These are the types of things that you do maybe once a year or once every few years. Just zooming into that a little bit better so you can see how that volume inside of here becomes this volume if you juxtapose those piston sections. Okay. Now, those are all great, but at some point people prefer to, I don't have to shut down. It'd be nice if I could add some clearance without shutting down the unit. Because every time you shut down, you got to purge all the gas, you lose that. It's bad enough you lost some money. But nowadays with emissions, you're blowing out all this ethane, and you're losing money and picking up emissions, which could result in fines and all that. So it'd be nice if we could add clearance dynamically somehow without shutting down the unit. The most common way of doing that is what's called a variable volume clearance pocket, a manual one. I'll zoom in on this one a little bit. And you'll see there's a hand wheel here that basically turns a screw, and that screw pushes this internal piston, the yellow item here, forwards and backwards. And by bringing it backwards, you're going to add more clearance to the inside of the cylinder. And if you push it forward, you're going to reduce that amount of clearance inside the cylinder. The advantage now is you're making an operation on the outside of the cylinder that's changing something internal without having to shut the unit down. Now, we say that some operators have told their operators to bring the unit down to idle before making these changes. Some companies allow their operators to make these changes on the fly. A few companies have even said you need to shut down the unit. You don't have to purge the gas, but you got to shut the unit down, make the changes, and bring it back up. So there's a variety of different ways that people use these, but at least in almost all of them, they don't have to purge the gas out anymore. They can make these changes one way or the other to add or remove clearance. So advantage is we're no longer purging gas. Disadvantage, however, is these generally only affect the head inside. Again, it's coming off the front head here. It's not something that you can readily put on the crank inside. All in all, it's fairly good for anybody that's tried to turn one of these. Remember, you have high pressure gas in here pushing on the screw, and it makes it very difficult to turn these at times. And because of that, people don't always use them as much as they should. Well, if something's great and doesn't get used because it's too much work, then we move on to, an electric, hydraulic, pneumatic version of that. And so Dresser, ACI, and Ariel Horbiger have developed what's known as automated variable volume clearance pockets. Dresser, ACI have a hydraulic one. ACI and Ariel have a pneumatic one, and Ariel Horbiger have a electric version of one. You're just using the other energy besides human power to stroke that piston back and forth. That's going to add or remove clearance to that head-end cylinder. So here's one of the ACI hydraulic versions of that. This is a Dresser ramp version of it. Now, the drawback of these is they're slow and they're very costly. Advantage of them, obviously, is now you're able to stroke that device and hit lots of different clearances in between them. So everything, like all these devices, will have their pros and cons. I'm just trying to walk through and give you an idea of what's out there today. Okay, another device, one of the drawbacks of the variable volume clearance pocket that's been automated is that piston moves back and forth at a relatively slow rate. There's a lot of moving parts. So ACI, Lawrence Berry developed a patent on this. ACI bought it from Gas Products, and we're continuing to develop this and make it better. It's a way of simulating that variable volume clearance pocket, but at the same time not have all the moving parts. Effectively, it's a valve here that exposes volume back here, but the valve is timed such based on differential pressure that only a portion of this volume is exposed. So if you just expose a little bit of it, it simulates adding a little bit of added fixed clearance. If you delay that longer, then it realizes more of this volume, and it simulates having a lot more clearance back there. But this type of device can generally actuate a lot faster, and there's no stroking mechanism. It's just a regular valve. Well, I shouldn't say regular valve, but a special modified valve here. But the big savings here is you don't have all those moving parts, and you don't have electric motor or stepper motor or things back here trying to move a large piston against heavy gas forces inside.
Dwayne, what was that called?
A stepless gas pocket. I don't know if Chad has a better name for it right now, or you'll hear more about this.
Ours is the gas pocket. Ours is the gas pocket, right?
Yeah. You'll hear sort of more about this in the next few months. Is the goal here. Okay. Then we hit the standards in the industry. These have been around for a long time. These are field proven, very cost effective, very useful. These are typically what we would call front head clearance pockets. So now, where before you had a fixed plug like this, and you either took the plug out and just put a cap on so it was all or nothing, but you had to shut down to do it. Now imagine a plug sitting in here that can seal against there with an actuator that can lift that plug up. When the plug's lifted up, now you can expose this volume inside of here, and then the actuator, when it pushes down, will push the plug down, seals it, and now this volume inside here is trapped and is no longer exposed to the cylinder. That's the essence of when we talk about automated fixed volume clearance pockets. It's just having a hole with a plug and an actuator that can seal it and open it or close it. It's the size of the hole, the size of the pocket, the number of the pockets, all of those would be kind of developed with the engineering team and the applications guys to find out how much is needed for this application. But ultimately, they all kind of fall in the same category. Just a volume with a plug to open and close it. And because this is strictly clearance with a nice standard actuator that has been around for 50, 60 years, this type of technology has been field proven with thousands and thousands and thousands of these types of devices out there.
Dwayne, it's Nigel. How is that calibrated, that actuator? I mean, is it done
Okay.
it operates on and off? I mean, how do you set it?
So, and typically you would look at, like, let's say the MAWP of the cylinder, what type of gas pressures are going to be in here. And then the nameplate over here will kind of give you some idea how much air pressure you would need on this piston up here, this magenta colored piston, to close that piston against the gas forces pushing back on this plug face here. Okay. Now, ACI makes what's called a special gas balance or balance plug here. It minimizes the amount of gas forces acting on this. Typically, the amount of air back here is somewhere between 70 and 120 pounds of air. Is how we try to size them up. But if you have higher pressure gas in here, you may need a little bit higher pressure air back here. Sometimes, if you have really high pressure gas in here, you may need discharge pressure gas coming back here to push against it to close that. So not so much a calibration, but a correlation between the pressure inside the cylinder versus surface area of these two versus the amount of pressure acting on each one to make sure it allows it to open via the spring and allows it to close via having sufficient air pressure. Obviously, if you don't have enough air pressure, it won't close this, and you'll have the clearance open all the time. If you have too much air pressure back here, it'll slam this shut, and after a while, you start chipping this metal and causing damage. So you do want to find something. I mean, these are rather robust, but obviously you don't want to go to either extreme of not having enough or having too much. And so ACI does put a nameplate on here with different air pressures and what they would overcome in terms of gas pressure on the backside. Okay. So the front head clearance pocket, now this one's a manual one. This is the type of stuff ACI loves to replace. So you see, and we'll talk about these ones here in a second, but if you go out to a compressor site and you see these, okay, I mean, the operators can turn this wheel and open and close that plug inside of this pocket. But again, it's a tedious manual thing to do. Whereas if this had a pneumatic actuator on it, then the whole thing could be done by a control panel. Because keep in mind that as an operator, I would have to come in here and change all of these to change it from one hardware configuration to another. I can't engage one of these every second. If I needed to change 5 of these, I'd have to manually screw this one in, come over here, manually screw this one out, manually screw this one out, and screw this one in or something. And there's going to be that time delay where I may be overloading the unit, maybe underloading the unit. I may have these in an odd combination and I'm overheating the cylinder end, only because it takes so long for me to manually change all these devices. As opposed to if you had pneumatic actuators on them. Those actuators typically engage in like half a second. So all of these can go ka-ching, and within half a second to a second, everything's exactly where it should be, and it's nice on the engine or the motor, and it takes away a lot of the safety concerns. So if you're out in the field and you see any cylinders with these manual turn wheels, this is a perfect case of, I'm not saying everybody needs them, but this would be a good example of a unit that could benefit from some automation, and that's where ACI really excels on replacing these types of manual devices with pneumatic ones. Okay, another type of clearance pocket would be one that's built inside the cylinder. Now these ones are very difficult to even know, because if they don't have an actuator on top, they would just have a cover. And from the outside, it could look like this is just a valve plate cover. The only way I can generally usually tell in the field is the valve plates, especially on older units, they paint the cylinders every 2 years. And if it's a valve cover, obviously they have to take the cover off, inspect the valve, replace the valve once or twice a year probably at least. And so you'll see the chipping of the paint on the nuts and around the ring here and the cover. If however, it's just a plate on a water jacket or it's a plate covering up an internal body pocket, they probably never take it off, and it's got 5 years of paint built up, and these nuts have never had the paint scraped off. So if you see a cover where the nuts have paint scraped off, that's probably a valve. If it doesn't, it's something else. Not always one of these, but it could be something else. But it's not likely a valve. But an internal body pocket would be part of the design of the cylinder itself. So it's not something you can add after the fact. But if ACI was going to replicate a cylinder that had one or design a new cylinder, and we could put one of these in there nicely, that's a nice feature to have. It's an efficient way of adding some clearance right there at the head end and or crank inside as you design the cylinder. Okay, the next one here is sometimes those front heads, as much as we'd like to put pockets on them, there may not be enough room to add all the clearance pockets that we need. So because of that, we sometimes have to add valve cap clearance pockets. Here, I'll try to, thought I had to zoom in on this one, but I don't. But both of these are valve cap clearance pockets. Sometimes you'll see the round bowling ball type clearance pocket like this one. Generally these are older cast ones. Today most of them are more cylindrical in shape, but pretty much the same. So the valve's down here, the valve's going to have a hole in it, but over the valve would be this clearance pocket. And again, there's just a plug that's going to seal or open up this volume, this cavity inside of this pocket to add or remove clearance from that cylinder in. But if we need more clearance, and the front head is not sufficient to give us all the clearance that we need, then we can put these pockets over valves. The advantage of putting them over valves is not only can you do them on the head end, but you can also do them here back on the crank end. And if necessary, now we try to avoid these because it's more difficult for the operators, but if necessary, you can actually put them over discharge valves down here at the bottom. We prefer the top because obviously they can bring a crane over here, hook this up, and lift it up and pull it. When you put them over discharge valves, generally speaking, discharge valves tend to be toward the bottom. So now they have to pull this out, which wants to fall down, and then try to grab it with a crane and angle it back up to lift it. So they're a little bit more difficult, not impossible to do, but just more difficult. So looking at this one, if there's sufficient room between the cylinders, we could, as a total, there's 2 valves per corner, so there's 2 suction on the crank, 2 discharge on the crank, 2 suction on the head, 2 discharge on the head. There's 8 valves that you could put pockets over, plus a large one on the front head. So there's a potential for 9 different clearance pockets on this. Now that's probably overkill in most applications, but we do have some pictures where we have cylinders where there are valve cap pockets over every single valve, plus one off the front head. Just because that application required that many clearance pockets to give them the control and the flexibility that they needed for their application. But again, as I mentioned, the size of these pockets and the location and the volumes inside of them and so forth, those are kind of best determined by ACI engineering and applications. But again, if you see anything in the field with these manual turn wheels on them, that's a great application to at least take a look at to see if they can benefit from automation and new clearance pockets. Okay, so as a recap here, some of the advantages of clearance devices is they tend to give you smaller, discrete steps. So when you go to unload a compressor, there's different ways of doing it. You can pinch suction pressure, you can recycle gas. Both of those are inefficient because you're losing energy. You can turn up or turn down speed, which is a great smooth way of controlling horsepower and flow. However, when it comes to the horsepower side, as you lower the speed, you're also lowering the amount of power that the engine can deliver. Okay, so it doesn't benefit you that much because you're lowering the capability of the engine at the same time you're trying to unload the compressor. So you're fighting both at the same time. So speed becomes a great flow control device, but overall it's not a good horsepower control device. However, speed is nice and smooth. Clearance pockets, however, tend to be more discrete. So instead of getting, half a percent change in horsepower, you're going to get a 4, 5, 6% change in horsepower. And most applications out there, what they would do is they would use clearance pockets to make the more discrete changes in power and flow, and then fine-tune the area in between by having a little bit of speed control. So if I had a 1,000 RPM aerial, I might open up a clearance pocket, which would drop me down 6%, and then I might raise the RPM up by 20 RPM to put me exactly at the flow that I desire. Because the pocket close might be slightly too high on flow, the pocket close might be slightly too low on flow. But I know the flow is somewhere in between there, so with a little bit of change of RPM, I can get exactly where I want. So it's nice to be able to mix nice discrete steps with smooth steps. It works out really well for automation. I just mentioned smaller steps here because in a couple of weeks when we talk about indie excavators, they're going to have large discrete steps. So pockets are nice and smaller discrete steps. Now you'll notice that that's a pro and a con, because sometimes if you want large steps, pockets can't give it to you. So when you want them, they're ideal, but if you want larger steps, that's where they may come up short. Okay. Another advantage of clearance pockets is they're fairly easy to retrofit on existing equipment because you can put them over valves, you can put them on front heads. As I mentioned at the beginning, clearance is the most efficient way to unload a compressor. Anything else we talk about, whether it's hydrocoms or indie activators, stuff like that, pinching the suction gas back, throttling, recycled gas, all of those are inherently inefficient. So if you want to keep your efficiency high, always use clearance devices. It's fairly easy to customize these ones because you can ultimately decide the size of those volumes, the number of them, and retrofit those onto the compressor of interest. And because they've been around for lots and lots of years, and like I mentioned, there's thousands and thousands and thousands of these out there, it's a well-proven technology. On the more negative side about clearance pockets, again, if you want larger steps, these may not always be the best option. The one drawback that you can get into is if you get too much clearance on a cylinder end. What happens there is if you get too much clearance, your PV card gets very skinny. Now, in theory, this is not a problem, but then there's theory and then there's the real world. In the real world, there may not be enough time, even though the curve looks beautiful, there may not be enough physical time to get this gas through those valves, in which case the gas doesn't actually leave, it re-expands because I didn't push any gas out, I'm not really going to pull any new gas in, and so the same gas is trapped on that head end or crank end the entire time. In a perfect world, it heats up, pressurizes, it cools down, and depressurizes. It's a perfect event. But because the real world has friction forces and such, every one of these strokes back and forth is going to cause a little bit of heat rise due to friction. And as a result, its internal temperature is going to build up. 100, 150, 200, 250, 300, 350, 400, 450, 500, 550. At some point, it's going to melt the valves, damage the rings, damage the seals, and so forth. Because this hot gas never leaves the cylinder, automation's temperature probes in the discharge flange never pick this up. So unless someone goes up there and touches the cylinder, they would not know that it's extremely hot because there's sensors down on the discharge flange picking up the other end gas. So we don't really want the PV card to get too skinny, and that's the one thing that can happen if you add too much clearance. So most OEMs will say don't go less than like 15% to make sure we have enough time to get the gas through the valves. So that's really, we call that low volumetric efficiency when that PV card gets too skinny. The other thing about clearance pockets is they're generally not that useful for very low or very high compression ratios. What happens on very low compression ratios is clearance hardly makes a dent. You can add a whole lot of clearance and barely change the horsepower or barely change the flow. On the other hand, if you have a very high compression ratios, just a little bit of clearance will significantly jump up the amount of horsepower or decrease it, or same thing on flow. So clearance is from moderately low compression ratios to moderately high compression ratios. That's the sweet spot for clearance devices. Really low, not so great. Really high, you got to be careful on those. Okay, any questions? That's all I got on slides.
Just one comment, Dwayne. Thank you very much. ACI serializes every actuator they do, and we're in the low 30s, I believe, 30,000. So we've done 30,000 plus actuators. So like Dwayne said, there's lots and lots of these out there.
This is Jim. There's also sales opportunities on those machines that already have those big, bulky-looking clearance pockets you see. They're often cast pieces of iron, but for replacements of their actuators, and we can do that too.
Yeah, and that's a good point, Jim. So when you see stuff like this, is one is we can just replace the actuator part here. The other is, this. At the same time, that's also a good time to take a look and see if they need more clearance or they need less clearance, and if you're going to make changes, now's the time to reevaluate the station and see what you can do to give the customer what they really need for their best controls.
Thanks, Dwayne.
Okay.
Yeah, thank you, Dwayne.
Okay.
Yeah.
Thanks, Dwayne.
Very good.